Good morning, class. We are looking at section 3.6, derivatives of log functions and on for the exam review, which covers from section 3.6 on all the way to 4.3. Derivatives of log functions. So let's put this in slide mode. We also like this. The derivative of ln x, we proved it's 1 over x using implicit differentiation. And in short, we flip over the function if we are interested in finding the derivative of natural log of a function, let's say f of x, then we flip that over and then multiply by its derivative, g prime of x. So ln of g of x, the derivative is 1 over g of x times g prime of x. If we happen to have a different base, that means it's no longer natural log, the base is no longer e, then by the change of base formula, we also have to divide by ln b. There are a lot of logarithmic formulas we should be comfortable with. First is the definition of a log, then the general form, then we have the specific form for base e, and then known as natural log, and then we have a common log. If you look at, for example, the first one, log of 1 with any base is 0. Obviously, if you go by the definition, b to the power of 0 equals 1. If you follow it in this manner, b to the power of 0 is 1. So that's what we use to understand this concept. Now, having said that, the second one says when the base and the argument are the same, the answer is 1. These two refer to the fact that logarithmic functions and exponential functions undo each other, they are inverse functions. Then we have the product rule, the quotient rule, the power rule, and the same thing applies here for the natural log as well as common log. Here's the change of base formula. All right, why is it important? When we want to differentiate for a basic case, it may not make much of a difference. But for a case such as this one or even that one, if we decompose the log, it makes life easier. So let's do that here. ln of the top minus ln of the bottom. Don't forget there's a 1/2 in front. So the very first step is to decompose that. Now, as far as the differentiation is concerned, ln of 1 over x, you flip that over 1 over 1 over x and then times the derivative of the argument, which is 1, minus 1 over 1 minus x times -1. Don't forget there is a 1/2 in front. Now, I'm going to assume everybody can finish that. The idea is very simple, that this one inside is 1 over 1 plus x. This one is plus 1 over 1 minus x. You can take a common denominator and finish the job by multiplying by 1/2, because the rest is elementary algebra. Number 6. We want to decompose this, which is the natural log of the top minus natural log of the bottom. Natural log of the top, ln of 5x, is ln 5 plus ln x. Therefore, when we differentiate, this one is a number, becomes 0. This one is 1 over x minus 1 over x squared plus 5 times 2x by the chain rule. Again, you take a common denominator of x times x squared plus 5. So 1 times x squared plus 5 minus 2x times x comes to the top, and it simplifies as follows. I'm assuming everybody can finish that, but let's quickly write the intermediate step as x times x squared plus 5, 1 times x squared plus 5 minus 2x times x. That's how we arrive at the answer. So here's the next one. You're dealing with a log again. So let's go with the steps that were mentioned. You're going to simplify this if you can. Simplification in this case, we can bring the 4 in front using the power rule. There is nothing else we can do to simplify it further. Now we work on this. So 4, we have it, and then the log, you flip this over, 1/9 minus x cubed. By the chain rule, we need the derivative of the parentheses or the argument, okay, which is negative 3x squared. Then this is log, this is not ln. That means we don't have a base e, we have a different base, namely common log base 10. So 1 divided by ln 10 by the change of base formula. So let's quickly recap. Here's number 4. Flip this over. Chain rule says differentiate this. Change of base formula says 1/natural log of the base, which is 10. So I hope you see the only thing at top is 4 as well as negative 3x squared. That give us negative 12x squared in the numerator. Because of this, we have a technique called logarithmic differentiation, in which case, where the function is complicated, we use logarithmic differentiation to differentiate, or if the base as well as the exponent are both functions, we go with that process. The very first step is take the natural log of both sides. So we're going to take the natural log of the left side is ln y, and natural log of the right side, sine x, becomes the coefficient. So this becomes sine x ln x by logarithmic property, the power rule. I'm going to put a raised dot in between, saying that the right side now, if I want to differentiate, I need to use the product rule, the product of sine x and ln x. So let's differentiate both sides. This is ln y. So what do? Flip this over, 1/y. But remember, y is the same as g of x, is a function of x, times y prime by the chain rule. Then we ignore this and we differentiate this using, as I mentioned, the product rule. Sine gives you cosine times ln x. Ln x gives you 1/x times sine x. Practically, you're done. All you have to do, get rid of 1/y. How? Multiply both sides by y. This goes away and y becomes the coefficient of the right side. So what is y? X to the power of sine x. We are multiplying both sides by y, everybody. In other words, if you want, this is in essence, so you can get rid of this and say this has to be multiplied by y. That's the idea. Rates of change, just reminding everyone that the average rate of change of y with respect to x is the good old slope. You have 2 points, find the slope. So if I have 2 points, I can calculate the slope rise over run, delta y over delta x, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. How do you write that? This is one way to write that. This is another one, or this one. Normally we call this the difference quotient, although in essence, all of them are the difference quotient, or f of b minus f of a over b minus a. It depends what you're dealing with here. For example, if this is x and this is x plus h, or this is a plus h, becomes something similar to that. Now, if we take a root, if we take a limit, okay, instantaneous rate of change, of delta y over delta x, we let delta x go to 0, or the limit of this expression with x in general and let h go to 0, that is the derivative function, the instantaneous rate of change of y with respect to x. So this is average, this is instantaneous differentiation. Let's look at this example. It's basically the elementary algebra stuff we've seen, and then it has a part that is calculus. We will get to it though. So the first part, very simple, very straightforward. The cost function is given, the revenue function is given. What is the profit function? Profit function by definition is revenue minus cost. Elementary algebra, subtract the cost function from the revenue function. Here's your answer. It's a good practice to put it in descending order. We want to evaluate all of the above, the cost, the revenue, the profit, when x is 50. We do that. We just plug in 50. I'm assuming nobody has any problem with that. It's, again, elementary algebra, everybody.
Ani.
So let's plug in with its C of 50, R of 50. Now, as far as P of 50, you have two choices. You can plug in, or just remember P is R minus C. You can do that, and you can come up with the same answer in the same manner. The marginal cost. The purpose of this question was to look at this concept known as the marginal cost. Marginal cost, or revenue or profit, the wording marginal refers to differentiation. That's really the bottom line. That's all that matters, and it does have an interesting meaning. So C prime of x, R prime of x, P prime of x, and then we plug in 50. So that's really the idea behind this question. Marginal cost. Let's find C prime of x. 62 times 2x. Okay, 124x. We want C prime of 50, plug in 50, do the math. R prime of x, 3x squared minus 24x plus 40, and plug in 50. Do the math. For P of x, we can do the same thing. P prime of x is 3x squared minus 74 times 2 minus 148x plus 40, and now plug in 50. For this, for either one, you can say P prime is R prime minus C prime, okay, or R prime of 50 minus C prime of 50. So you could use the previous two lines to get to the answer. So when 50 units have been made, the approximate cost of the 51st unit will be $6,200, and the approximate revenue from the sale of the 51st unit will be $6,340, for an approximate profit of the 51st unit of $140. I want to make sure everybody understands what we're referring to. If you were to find the cost for the 51st unit, precisely would be C of 51 minus C of 50. What we are saying is this is almost equal to C prime of 50. I highly recommend you guys try it on your own. This was really the purpose of this question. Marginal cost, marginal revenue, and marginal profit, they give an approximate cost, revenue, and profit from the next unit. In this case, if we are looking at 50 units, then 51st. Here's another example. We want to look at the distance is given or the position function, S of t. T is time in seconds. What is the velocity of the object from 2 to 4 seconds? This is the average velocity, everybody. So basic algebraic formula will do the job. S of 4 minus S of 2 over 4 minus 2. So we wouldn't worry about that. It's 7 meters per second. But what is the instantaneous velocity and acceleration? Instantaneous velocity, we need to differentiate this. So 4t minus 5, that's v of t or s prime of t. After 6 seconds, replace the t with that, gives you 19 meters per second. Now, acceleration is defined as the second derivative of the position function or the first derivative of the velocity function. In other words, differentiated again. We end up 4 meters per square second. By the way, because it is a constant, we don't have to plug in 6. If it was not, we had to. Remember, this is dv dt. I want to discuss the units for you. S double prime or v double prime means dv dt, and the units become the units of the numerator, which is meters per second, over the units of the denominator, which is seconds. So meters per second per second. When does the object reach 31 meters per second? That means the velocity is given. A t is missing. Very straightforward. I want to remind you of exponential growth and decay that we have seen in intermediate algebra. And as far as the calculus is concerned, when dy dt is k times y, okay, that means the rate of growth depends on the population. Then it follows this exponential format, and we've been through that. Dy dt is ky or dp dt is kp, okay? So a equals p e to the power of rt, y equals y sub 0 e to the power of rt, so on and so forth. You have seen many different formulas. Any of them that you use is fine. Different texts, they use different formulas. Couple of things we want to add. This equation sometimes is called the law of natural growth. When k is positive, I want you to pay attention to this. When k is positive, it's an exponential growth. When it's negative, it's exponential decay. And that's all there is to it. You could use the same formula for both. Automatically, when you go through the process, the exponent becomes negative for the decay and positive for the growth. We also have the Newton's law of cooling, which tells us the temperature at time t is y sub 0 e to the power of kt plus t sub s, where y sub 0 is t sub 0 minus t sub s. T sub s is the surrounding temperature. Y sub 0 is the difference between the initial temperature. T sub 0 is the initial temperature and the surrounding temperature. We have discussed that in our PowerPoints. Let's look at a couple of examples regarding this matter, especially in the case of exponential decay. I want to again emphasize that if we use y equals c e to the power of kt, we are using positive here. The half-life will become minus ln2 over k. If we use ce to the power of minus kt, in other words, we are writing the negative sign, then half-life becomes ln2 over k. Okay, so you want to pay attention to that, as I mentioned, depending upon what text you're using and in what context, the formulas are ultimately the same. Now, a sample contains 1 gram of radium. How much will it remain after so many years? Given the fact that the half-life is 1,620 years. So let's use one of the formulas. It doesn't matter which one. It's important to know ultimately this is an exponential decay, so the exponent will have a negative sign if you do it properly. So if we use this formula, okay, and the initial value, remember, see, if you replace the t with 0 class, this goes to 1, this becomes the initial value. That's why many times they call this y equals y sub 0 e to the power of kt. Again, like this one, m of t is m sub 0 e to the power of kt. That refers to the fact this is the initial value. So having said that, with the half-life of 1620, you can plug it into this general formula and write half-life, so half of c. You don't even have to change the c. Is equal to c e to the power of k. You can even keep that as a t or even h and do the math. That's what brings us here. So you can drop the c. Now, if I take the natural log of the left side is equal to the natural log of the right side. Now, the left side is ln1 minus ln2 and ln1 is 0. Therefore, k is the left side minus ln2 divided by 1620. Minus ln2 divided. You can, we went over that, I wanted you to see that, but I want you to take a look at the formula that I gave you up here. Minus ln2 divided by k. So what was k? 1620. You could have used that formula. I just wanted to show you in case. So how much do we have after 1,000 years? Let's write the formula in general. What is this? Remember, we have a c here and c is equal to 1. So we write the formula y of t is equal to the initial value, which is 1 e to the power of negative this value, 0.0004279 t. Replace the t with 1,000 and do the math. 0.652 grams. A quick recap. I want to make sure we understand what's happening here. The general formula, if we use this one or this one, this m sub 0 or c refers to the initial value. We can develop the formula for half-life. H becomes minus ln2 over k. If we don't put a negative sign here, if we do, becomes ln2 over k. I wanted to show you step by step how we arrive at it, and I wanted to show you that the formula works. And that's really the key behind this question. The rest is elementary algebra. Newton's law of cooling, I had given this in my PowerPoint, so let's quickly look at this. A dead body was found at 1:30 a.m. The temperature was 55 degrees, and the body temperature, this is the temperature which is known as the surrounding temperature. The body temperature is 87 degrees. So what do they do? The forensic, if you will, when they show up in order to estimate the time of death, they wait some time, for example, in this case, 1 hour, and they measure the temperature again. Now it's 85 degrees. They can do the calculation and estimate the time of death. So we are going to do that. And then from there, we're going to see who is probably at fault. So let us write the given. That's important to understand. So at 1:30 a.m., we're going to see that this is the time that we're going to start. The temperature, which is 55 degrees, refers to the surrounding temperature. What is the temperature of the body? 87 degrees, we call it T sub 0, which is the same as T of 0. T at time equals 0. Now, so T sub 0 is 87. Then 1 hour later, that means 60 minutes later, it's 85 degrees. This is the given. This is the translation of the question. So let's go with this formula and plug in what we can. Remember, y sub 0 is the difference between the two. T sub 0 and T sub surrounding. T sub 0 and T sub surrounding. Their difference is 32. So we have this formula. This formula, class, T of t is 32 e to the power of kt plus t sub s. So this is the formula. And as you can see in this formula, we found y sub 0 by the fact that it's t sub 0 minus t sub s. If you plug in, I've gone over that. If you plug in 0, class, t of 0 is, remember, you replace the t with 0, you get 1 here, you get y sub 0. I'm looking at this t if you change it to 0 plus t sub s. And t of 0 is called t sub 0, and that's how it gives us this formula. Having said that, we know that this is the formula. We are going to use the second piece of information to find the missing k. T of 60 is 85. So if we replace the t with 60, this becomes 85. We are going to calculate that. Now, this is intermediate algebra. K is equal to that. How does it work? Just quickly subtract 55, divide by 32, take a natural log, okay? I hope everybody is fine with that. From here to here, you need a couple of steps, so that shouldn't be a big deal. You can drop this and change this to 30. Then let's just write e to the power of 60k is 30 over 32. Again, I don't want to even simplify. There's a reason I left it as that on purpose, so I can see where the numbers come from. Needless to say, we can divide by 2. Now, if you take a natural log, okay, the left side, so let's do that. If I take the natural log of the left side, so ln of the left gives me 60k, and ln of the right gives me ln of 30 over 32. And now you divide both sides by 60. You have this, and therefore you have your formula. That's really the bottom line. This is elementary. It shouldn't be any problem. We know intermediate algebra, and that can easily give us the answer. This is the general idea. Now, what is a normal body temperature? The assumption is that it's 98.6 degrees. By the way, recently they have noticed it's slightly different, but we're not going to get into that. So assuming it's 98.6 degrees, we want to see at what time it was 98.6 degrees. That means at that time it was alive. That's the idea. So we're going to set this equal to 98.6 and solve. I'm going to assume you can solve that. You subtract 55, you divide by 32, you take a natural log, all of the above. So you go through the process. There are a couple of steps. I'm going to leave it for you to handle it. And we end up with minus 288 minutes, which means from the time 0, which was 1:30 a.m., minus 288 minutes, the body, the person was alive, and we are going to subtract this from 1:30. Gives us 8:42. So according to this calculation, at about 8:42, the person was alive. So when you look at that, Scrooge had an alibi for 9 p.m. after. That's a problem. From 8 to 9:30, so she's in good shape. Sat until 11. So you see who did the job. And that's really, believe it or not, what forensic teams do. And so that's the beauty of math and calculus. Related rates. We discussed that in order to find a relationship between two quantities that are changing, we need a formula first that relate the two, and then we use the chain rule and differentiate to find the related rate problem. So as an example, if you look at this one, a 20-foot ladder leans against a building, the base slips away at a rate of 2 feet per minute. We want to see the rate at which the height is changing when the base is 12 feet from the building. So let's look at the setting. It's important to have the drawing. So here's the setup to begin with. It's going to move this way. As it moves this way, so this, if this represents x, x gets larger. So that creates what's called dx dt, and the tip is coming down. If we call this y, it gives us dy dt, if you will. Okay, so what is given? This is fixed at 20 feet. The base is slipping away this way, so dx dt is 2 feet per minute. Coming down, we are looking for dy dt when x is 12 feet. What else can we say? This is a 90-degree angle. So a squared plus b squared equals c squared. So that means x squared plus y squared equals c is fixed at 20 squared. So a piece of information from geometry or algebra, if you will, Pythagorean theorem. We are differentiating this part. I hope you realize the most important part is the translation, being able to come up with the setting. This gives us 2x dx dt plus 2y dy dt. The right side is a number, therefore 0. So when we look at this, we see that everything is given except y. So if you put the x, it's fixed at x equals 12. If you put that here, you can find the value of y using Pythagorean theorem. So the y is missing. We calculate it, and now we can plug in everything. We have everything. Let's put it in. X is 12, dx dt is 2, y, we found it to be 16, 2 times 16, dy dt is missing, we solve for it, and we end up with -3/2. Now, as far as the units are concerned, feet per minute, I want to discuss the sign. As you can see, x is increasing, dx dt is positive, but y is decreasing, therefore dy dt must be negative, and it is. Here's another one. A spherical balloon is deflating, losing 8 cubic centimeters of air per minute. At the moment when the radius is given as 20 centimeters, how fast is the radius? Changing, positive means increasing, negative means decreasing. In case they may give us the wording changing and the sign tells us what's going on. This is a formula you're supposed to have. The volume is 4/3 pi r cubed. We have dealt with that before. So what is given? The reason I picked this question, because dV/dt is given, and because of deflating or losing, that means negative. At the moment when R is 20, okay, we want to see dr/dt. So the translation goes as follows. This is the volume. dV/dt is negative 8 cubic centimeters per minute. When R is 20, dr/dt is missing. We have done this before, so let me just quickly show you. When you want to differentiate this, dV/dt is 4/3 pi, and then r cubed, 3r squared, dr/dt, and we write it as 4 pi r squared, dr/dt. We can either solve for dr/dt, or we can just plug in just the way it is. So let's do that. Replace this one with -8. Divide both sides by 4 pi times 20 squared, which is 400, and times 4 is 1600. The 8 goes away. And 1600 becomes 200 pi. This is the precise answer. Negative 1/200 centimeters per minute. You can go with that approximation, but you must always write the exact answer when it comes to calculus. Exact answer, always. There's another one. A cylindrical tank with radius of 10 meters is being filled. The rate is 7 cubic meters per minute. We want to see how fast the height is changing or increasing. Again, it's important to pay attention to the sign. The sign tells you whether it's increasing or decreasing class. So you are looking at a case like this, where the radius is fixed at 10 meters. By the way, we are supposed to know the volume of a cylindrical shape, pi r squared h, the area of the base times the height, everybody. So this is fixed at 10 meters. The volume is pi r squared h, dV/dt is 7, and you write the units, cubic meters per minute. How fast is the height? So dH/dt is missing. And we know that this is at 10 meters, fixed at 10 meters. Now, let's do the math. Again, the important thing is the piece of geometry that hopefully everybody remembers, the area of the base times the height. We want dV/dt. And what's happening now? It is important to know that this is using the product of R and H. If R was a variable, then you have to use the product rule. However, R is fixed at 10. You have a choice. You can just keep it at R and at the end change it, or right now change it to 10. Either way makes no difference. I'm going to do both ways. I want to show you the idea behind the 10. If you keep it, and I put a capital R just to mention that it's fixed. So if I'm differentiating this, pi r squared is not going to go away because it's fixed, and h gives me dH/dt. If we go this route, then dV/dt is given as 7 or is given as 10, find dH/dt. 10 squared is 100, so 7 divided by 100 pi. This is again an exact answer. However, we could go back here, replace the R with 10, and that gives us 100 pi h. That may even be a faster and better way. I wanted to show you both ways. And the reason, again, in case we don't have a fixed R, in the case of a cylindrical shape, of course we do. So the V is 100 pi h. And now if you differentiate both sides with respect to time, this is dv dt. This is fixed 100 pi, so h gives you dh dt. And that gives you exactly the same answer. That may have been a better approach, but in case you've seen that and you want to stick with that, as long as you realize the radius is fixed and you stick with that, that works out. Here's the next one. The idea of a differentials, okay, we want to make sure that we distinguish between a differential and delta y. Delta y is the change along the y for the curve. Dy is change along the y-axis for the tangent line. Therefore, let's just give it a, let's call this point C. So delta y is equal to BC, whereas dy equals to AB. And as you can see, AB and BC obviously are not the same. However, as delta x, this is delta x, everybody. Delta x, if we call this D, let's say, delta x is identical to dx, and it's the run. Or we call this d, right? So pt. When delta x gets smaller, the approximation gets better and better. So dy is f prime of x dx because dy dx is f prime of x. So let's go through the process quickly. F prime is dy dx. dy is precisely f prime of x dx. Delta y is the run along the curve, f of x plus delta x minus f of x. And we can approximate that by this. The approximation gets better as delta x gets smaller. So delta y is precisely this. Dy is precisely this. Take a look at delta y versus dy. They are not the same. However, because f of x plus delta x is f of x plus delta y, sometimes we approximate the delta y by dy, and this becomes this. Now, linearization refers to finding the tangent line at a given point. That means really stick with the point slope. The rest of it is really elaborating on the concept where the pair x sub 1 and y sub 1 is the same as a f of a. In other words, in this case, a f of a would be x sub 1 y sub 1. F prime of a is m. Do you have to memorize it? No, I would stick with this formula. So linearization means find the tangent line at a specific point. All right. Having said that, let's look at the differential for this one. Simply put, dy is f prime of x dx, so you can ignore what dy is for now and find y prime or dy d theta, which means you're looking at a natural log, flip it over 1 over sine theta by the chain rule times the derivative of sine, which is cosine. Cosine over sine is cotangent theta. That's y prime or dy d theta. So what is dy is the same thing times, see, f prime of x dx. In this case, we're going to say times d theta. Because the independent variable is x, here we say times dx, but the independent variable is theta, here we say d theta. Again, ignore the question first. Let's differentiate y prime or dy dx using the quotient rule. I hope everybody remembers the quotient rule. F prime g minus g prime f over g squared, where the top is f, the bottom is g. So the top gives you e to the power of x times the bottom, minus the bottom gives you negative e to the power of x times the top, and the bottom, just write it in a parenthesis with squared. Now you apply this, these two cancel each other, so you end up with e to the power of x only. I'm assuming everybody can go from here to here. It's algebra class, fairly basic. And therefore, dy is f prime of x times dx. dy is the same thing times dx. We want to use differentials to approximate 51 squared. That means we need two things. First, a function. By the way, 51 squared, you can say 50 plus 1 squared and do the math, a plus b quantity squared, which is a squared plus 2ab plus b squared. You end up with 2601. But 51 squared, you want a function. By reading it, 51 squared, the function f of x is x squared. You want a number very close to that, that you can easily square. Obviously, 50 squared is just 5 squared, 25, and you put 2 zeros. So that would be the case. So you want the function. So as you read the question, 51 squared, that means x squared. Closest number would be 50, and delta x would be the change, which is 1. It's important to see that from 50 to 51, we had a plus 1 dx. If we are interested in calculating, let's say 48 squared, just for the sake of argument, I mentioned that in my PowerPoints. For example, if I want 48 squared, then delta x or dx is -2, which means we want to be very careful or we don't come up with the correct answer. In other words, the result for this is less than 50 squared. The result for this is larger than 50 squared. So sticking with that, we need to find f prime of x, which is dy dx, to be able to use it here. Okay, so we have f of x, dy is missing. So what is f prime to x? What is dy? The same thing times dx. So therefore, we replace the f of x with x squared and dy with 2x dx. What is x? 50. What is dx? 1. Plug in, calculate, and the approximation is 2600. As I mentioned, if you compare it to the actual one, they are extremely close. And the reason why is very simple. Delta x is very small in a matter of comparison to x. The second method is that here's the function. Find the tangent line at x equals 50. Okay, which means you need two things. We need a pair. So x is 50, y is 50 squared, or 2500. So here's your function. Here's your number. So the pair would be 50 and 50 squared. You also need the slope. So how do you find the slope? So we want to find the tangent line, everybody. We need f prime. It's given 2x. If I plug in 50, that becomes the slope. So I've done the work already. We don't want to waste time. This is in case we go with that formula as I mentioned that. So I hope you realize that m is 100, right, class? So stick with this formula. Y, let me just write it actually here so you see what I mean. Y minus 2500 m 100 times x minus 50, and you finish the job, you end up with this. Y equals this, which we call it the linearization. Now, what do we want? We want linearization at 51. Replace the x with 51 and you're done. It's that simple, everybody. Linearization as well as differentials can be used to solve this question. One side of a right triangle is known to be 20 centimeters. So one of the legs. And the opposite angle is 30 degrees, maybe with a possible error of plus minus 1 degrees. We want to use differentials to estimate the error. Okay, in this case, we're really looking at the error, dx, dy, so on and so forth. So dy or dx, depending upon what you're dealing with. In computing the length of the hypotenuse and what is the percent error. So let's do the drawing first and foremost. So one leg, if this leg is 20, okay, and the opposite angle is measured as 30 degrees. Here's the opposite angle. The reason we don't put 30, because we have a possible error. So let's say theta. Okay, and theta is 30 on a regular basis. So this is the opposite angle. So here's one leg, here's the opposite angle. And then when we say possible error of plus minus, that means d theta is plus minus 1 degree. D theta is plus minus 1 degree. And for part A, we want to use this to find the error in computing the length of the hypotenuse. We want to error in computing this side, which we called x. Therefore, we want dx. So one leg is 20 centimeters. The opposite one, we're going to call it theta, which is 30 degrees. D theta, the error is plus minus 1 degrees. And I'm going to go with plus minus pi over 180. I'll tell you in a moment why. And we are interested in finding the x. Now, why plus minus 1 over pi over 180? Because in calculus, everything is measured in radians. Okay, so that's how you do the math. So we want to find a relationship between what is given and what is missing. So we want to find a relationship between theta and x. And I hope you see that sine theta is the opposite over the hypotenuse. We're going to stick with that. Sine theta is 20 over x. Therefore, x is 20 over sine theta. Class, we want to solve for x because we want to get to dx. X is 20 over sine theta, and that means 20 cosecant theta. If you want, I can write it for you. This is, from here, you can say x equals 20 over sine theta. And we want to avoid the quotient rule. That's why we put it this way. Therefore, if I go with dx d theta, class, we are going to remember x is a function of theta according to this, and that's what we want. Therefore, we can find the derivative of this function, dx d theta, okay, which is 20, and cosecant is negative cosecant cotangent. This is the answer. Remember, dy is f prime of x dx, therefore dx is the right side times d theta. Now replace the theta. So we want minus 20 cosecant. So let's change that to 30 degrees now. Change that to 30 degrees now, and change that to this. That's what happens. Now cosecant theta cotangent theta. Remember, cosecant is 1 over sine. What is sine of 30 degrees? 1/2. What is the reciprocal of that is 2. cotangent of 30 degrees square root of 3. D theta is the number. So again, if you want this one class, 1 over sine 30 degrees, okay, that's how you, and you can evaluate that. You end up with plus minus 2 square root of 3 pi over 9. If we want to approximate it with the decimal, we can do that. I highly recommend you stick with that, or at the very least, report both of them. The next thing is the percentage error or the relative error. Okay, so okay, we found that. What is the rate of error? What is the percentage error? Is the total amount of error, which is dx over x. If you remember that from elementary algebra, relative error is defined as the total amount of error, which is dx, over the actual amount, x. And so the relationship between the two is as follows. How do we know dx from here? How do we know x? Okay, let's look at this one. Let's look at this one, everybody. Sine theta, we said, is what? Sine of 30 degrees, or 1/2. Sine theta is 1/2. So 20 times 2. I hope you realize 20 divided by 1/2. In essence, x becomes, I have it here, x is 20 divided by sine of 30 degrees, which is 1/2. 20 divided by 1/2, 20 times 2. So simplify that and you get to the answer. Plus minus 0.03 or plus minus 3% roughly. The next thing, we want to look at the hyperbolic function. I'm going to remind you some of the formulas that we have seen in pre-calculus, and then we add a few more formulas from calculus. The most important definitions are these two. Cosh is defined as e to the power of x plus e to the power minus x divided by 2. Sinh is the same thing with the negative in between. So this is where we start. If you remember, this was the starting point, everybody. Now, then there are some definitions that follow really trigonometric definitions. If you remember, tangent was sine over cosine. So hyperbolic tangent is sinh over cosh, and so on and so forth, the rest of it. Then the derivative, they are similar to trigonometric functions. They are not identical. For example, the derivative of sine is cosine, the derivative of sinh is cosh. The derivative of cosine is negative sine, but the derivative of cosh is sinh. So there are some formulas here. Some other identities, if you remember, sine of negative x was minus sine x, and cosine of minus x was cosine x. In other words, sine was an odd function, cosine was an even function. The same thing works out here. And there are more formulas here, their inverse function. So let's look at a couple of examples involving that. Starting with cosh squared minus sinh squared, that we said is equal to 1. It's a very important identity. So let's prove that. And to prove that, if you recall, we did the same thing in trigonometry. To prove new things, we use the old stuff. So we're going to use these two, and we're going to plug them in. I'm assuming we can square this easily. You can square this one, e to the power of 2x, then 2 times the first times the last. I hope you realize the product of the two is e to the power of 0 is 1, and e to the power of minus x to the second power, that means e to the power minus 2x. Same thing happens here. If you combine the two, everything cancels out except 2, and minus 2, 4 in the numerator. We have this as the answer. Prove this one. We are going to start with the one we just proved, and we are going to divide, because we want this one to be 1. So we're going to divide this one by itself. So we divide everything by that. So we are dividing both sides by cosh squared, and it basically gives us the result. We want to differentiate, and I have the differentiation formulas for you here. I hope you realize. For now, you can, the way you read it, sinh, and you can pause. So you want the derivative of sinh, which is cosh. So cosh of 10x squared. So if we were to do this, I would say cosh 10x squared. Okay. Now, by the chain rule, I need the derivative of 10x squared. 20x, and we put it in front. That's it. We do the same thing here, and we change, if need be, this to the x to the power 1/2. We've done that before, so we don't have to worry about it. So by that, I mean we've dealt with the square root of x. Cosh gives you sinh, so sinh x to the power 1/2 or square root of x. And then the derivative of x to the power 1/2 is 1/2 x to the power of negative 1/2. This we have done this before, so this part, class, okay, it's 1/2 x to the power of 1/2 minus 1 or negative 1/2, which gives you this, and you put it in front accordingly. Okay. Hyperbolic tangent. So it's hyperbolic secant. So hyperbolic secant, the same thing squared, of course, right? And then by the chain rule, you need the derivative of the parentheses, which is simply e to the power of 2x, okay? It's said times 2. So hyperbolic secant squared, the same thing. And then the derivative of this piece is e to the power of 2x times 2. We're going to put this in front. And that is the final answer. For the inverse function, we have some formulas similar to trigonometric inverse functions. For example, the derivative of sinh inverse is 1 over square root of x squared plus 1, so on and so forth. So if we are interested in finding this, first and foremost, understand this is x, but if by any chance we change this to u as an example, let me just write this u or g of x, if you will. Let me use this one. So if instead of x, we have a u, which is the same as g of x, everybody, then this changes to 1 over the square root of, now x changes to u, and then we need g prime of x, du dx, or g prime of x. That's the idea. Therefore, if I'm differentiating this, so I'm going to follow this 1 over square root of x squared. So I'm going to square this one. I get x to the power of 4. So remember, this is u now. You can literally replace it with u. Square that, you get x to the power of 4 and plus 1. So that's done. Then we need du dx. What is the derivative of this guy? 2x. And you just rewrite it. To understand this better, let's look at this example. We do exactly the same thing. U is tan x. So 1 over the square root of u squared, that means tan squared x plus 1. And then we put the du dx, the derivative of tan x, secant squared. So follow this, everybody, secant squared. We are not finished, but that's the main part that matters. That is sort of new. Now, everybody remembers tan squared and 1, they add up to secant squared. I hope you remember that. So this becomes secant x, and with the secant squared, they cancel each other. And the reason we use a absolute value, because this is actually secant x in an absolute value. Okay, class? I hope you remember that square root of, let me just write that, square root of x squared is not equal to x is equal to absolute value of x. We've discussed that. Here's the last one for this. We want to differentiate this using the product rule. So I'm going to put a raised dot in between. So e to the power of x gives us e to the power of x times the second piece. So again, there's a raised dot here. Let me actually put that one in. And the second part, so this part, e to the power of x times cos x. Now cos x gives us sinh x times the first part. Practically, we're done with the calculus part. Now simplification, we can factor out e to the power of x. Now you may recognize or not from over here that what happens when we add them up. You can actually add them up. I hope you see that if you add them up, this one cancel each other, this one and this one, they add up to 2 e to the power of x divided by 2, which is e to the power of x, and then e to the power of 2x would be the final answer. Now, we're going to continue to chapter 4, application of differentiation. Again, a lot of differentiation formulas. Hopefully we are comfortable with. Let's get started here. Definition of a critical point. You find f prime of x, and where f prime is 0 or f prime doesn't exist, that's where we find the critical point. So for example, if we want this one, the steps are finding f prime of x. So x to the power of -2 is minus 2x to the power of -3 times ln x. You can put a raised dot in between if you want. And ln x is 1 over x times x to the power of -2. So your first step is differentiation. Using the product rule. Again, a quick recap, x to the power of -2 gives you -2x to the power of -3 times ln x. Ln x gives you 1 over x times x to the power of -2. Simplification. We can factor out x to the power of -3. We can rewrite this as this over x cubed. So that's so this is calculus, everybody. There's a lot of algebra involved. Now the next step is f prime is either 0 or f prime doesn't exist. F prime 0 when the numerator is 0. F prime doesn't exist when the denominator is 0. So let's look at the numerator and set it equal to 0. F prime equals 0. A fractional expression is 0 when the top is 0. So this is equal. So ln x is 1/2 minus 2 ln x plus 1. We are setting the numerator equal to 0, and ln x becomes 1/2. So what is x? Go with the definition. X is e to the power of 1/2. So that's the answer. The second part, f prime doesn't exist. We're going to look at this part. F prime doesn't exist in a fractional expression when the denominator is 0. So f prime doesn't exist only when x cubed is 0 and x becomes 0. However, that's not acceptable. Why is that? Because it's not in the domain. when you look at f of x, everybody? The restriction is ln x. So you can rewrite this as ln x over x squared. And I hope you remember, in order to find the domain, you look at the restriction for each one. This is a combination, if you will, of a rational function and a logarithmic functions, and the domain for natural log is 0 to infinity. So that's not included in the domain. 0 is out because it's not in the domain. So in short, and the synopsis of what we just did, find f prime, set it equal to 0, f prime doesn't exist, the ones we are looking for. All right, we want to find the absolute max and mean. For this case, we are looking at a closed interval theorem. In order for you to use the closed interval theorem, first you have to look at where the function is continuous. This function is a polynomial of degree 2 times 3, degree 6. The domain is all real numbers, therefore it's continuous from -1 to 2. First, you have to establish that. Now the process, find f prime, set it equal, take it from there. So what is f prime of x? 3 times the same thing squared by the chain rule times the derivative of the inside, which is 2x. When you set this equal to 0, this gives you 0. X squared minus 1 is 0, gives you plus minus 1. This part gives you plus minus 1. So we have three answers. Plus minus 1 from here, 0 from here. You're going to check to see if they are in the domain of interest. -1 is one of the endpoints. +1 is in between, yes. 0 is in between, yes. Plug into the original function. -1, 2, those are the endpoints. +1, 0, and come up with the answer. What does it mean? Largest number is 27. So absolute max equals 27. If they ask you where, at the pair, 2, 27. Smallest one, -1. Absolute mean equals -1. Where? At 0, -1. So you want to pay attention to the way they want you to answer. It is extremely important, class, okay? Where do they want you to write that? Do they want the absolute max only, or they want the absolute max at a specific point? So you want to be very careful with that. So having said that, we're going to quickly repeat a similar question. I don't want to spend too much time on that. I want you to recognize this is a cube root that is being raised to the power of 2. If need be, you can rewrite this as cube root of x squared. So the domain is all real numbers. Therefore, it's continuous from -2 to 3. That's the first thing. So it's a cube root function. So the domain is all real numbers, continuous from -2 to 3. Let's find f prime of x, which is 2/3 x to the power of -1/3. Can write it this way. So f prime is 0. Look at this expression, class. When you are dealing with a rational expression, f prime is 0. The expression is 0 when the top is 0. The top is a number. Doesn't matter, 2, 10, or -1 or 0.1. It's a number, can never be 0. F prime equals 0. Doesn't have any solution. F prime doesn't exist. It can be 0 at x equals 0. Is 0 in between? Yes. So plug in -2, plug in 3, plug in 0. Of course, 0 gives you 0, -2, you have to calculate it, and so on and so forth. So when we plug in, the end points give us these two numbers, and 0 gives us 0. Obviously, the absolute max is this, at this pair, and this is the smallest one. Here's the absolute mean equals 0 at 0, 0. Again, 3 to the power of 2/3 or 2.08008. That would be nice to write the exact answer. The Rolle's theorem, in short, has 3 parts. So if you're looking at the Rolle's theorem, you must mention the function is continuous in a closed interval and y, differentiable in an open interval and y. You also have to show the endpoints f of a and f of b are equal. Therefore, there's a number in between such that f prime equal to 0. So for the mean value theorem, we really have the first two, not the third one. Okay, if f is continuous on the closed interval, okay, differentiable on the open, then f prime is f of b minus f of a over b minus a. Let's just look at that. I want to explain the difference between the two. I have it in my PowerPoint again. The mean value theorem says if you have a continuous function and a differentiable function from a to b, and if you connect a and b, okay, the points, if you connect them, it gives you what we call a secant line. Because it's continuous and differentiable, somewhere in between, there is a tangent line parallel to that. If this tangent line is parallel to that, what does it mean? The slope of this line is equal to the slope of this line. What is the slope of this line? F of b minus f of a over b minus a. Therefore, somewhere there, in this case, this point has a derivative which is identical to that. Okay, class? That's the meaning of it. Mean value theorem. Okay. F is continuous in a closed interval, differential in an open interval. There is a number in between C such that f prime of C is equal to this. That means there is a point in between such that tangent line is parallel to the secant line. Now, imagine this is equal to 0. That means f prime equal to 0. That is the third part, which gives you the Rolle's theorem, and then it becomes a tangent line which is horizontal if we add the third part. So I hope it's clear to everybody. Now, here's a simple question. F of x is given. We want to find all sane intervals such that f prime is 0. The Rolle's theorem. So you have to look at the first part. We are going from a to b. A is -2 class 2. This function is continuous and differentiable in the closed and open interval simply because it's a polynomial of degree 4. So you have to write the following. F of x is continuous from negative to positive infinity, therefore it's continuous from -2 to 2. Same thing, differentiable. And both of them, the reasoning is very simple. Poly of degree 4. That's the reason. Now, for the Rolle's theorem, everybody, we have to show f of a equals to b. We have to plug in -2. This is a. We have to plug in b or 2. They happen to be identical. Either one results in 8. So we have the first one, we have the second one, we have the third one. If we have all three, then somewhere in between f prime must be equal to 0. Basically, you take the derivative of this function and you set it equal to 0 and it gives you the answer, and any number in between is acceptable. So here's f prime 4x cubed minus 4x. To set equal to 0, you're going to factor the 4x out. This gives you x equal to 0. This gives you x equals plus minus 1. I'm assuming everybody is okay with that. There are 3 answers. Any of those in between is good. If it's out, you don't count it. As you can see, all of those numbers are in between. So practically we're done. So find all C in the interval such that f prime is 0. So at this point, x equals -1, 0, 1, f prime is 0. You're done, but if you look at the graph, everybody, so be it. If you were to graph this, I'm assuming we are okay with graphing this function and drawing the tangent lines at that. One of the things I want to mention, because it's coming up, the concept of a graph. Remember the end behavior. The end behavior follows the leading term. The leading term is x to the power of 4. So it looks like that, just like x squared, because the degree is even. I hope everybody remembers that. So the mean value theorem, we have the following function, and in the mean value theorem, the third part is missing for the Rolle's theorem. That means we have the continuity, we have the differentiability, and that's all. So somewhere in between, f prime of c is f of b minus f of a over b minus a. By the way, if you do the cross product, you get to this. Either one is fine. So here's the function. We want to find all c in the interval of 1 to 4 such that the slope of the secant line is equal to the slope of a tangent. And that's really basically what it says. And I hope you realize that this is easy to look at as far as the graph is concerned. So by the way, this is a rational function. You got to graph it. I don't want to go over the graph. It's a rough sketch of the part that we are interested in from mainly 1 to 4. So there is a line parallel to that. We are looking to find this point. That's the idea, class. So this is the point we are looking for. That's the idea. Now, f is continuous and differentiable. Continuous in a closed interval, differentiable in an open interval. Why is that? I hope you realize this is a rational function. It's a rational function. And the domain is all real numbers except x equals 0, because it's 5 minus 4 over x. Okay, class? 5 minus 4 over x. Therefore, it's continuous everywhere, in essence, in everywhere from negative infinity to 0, union 0 to infinity. And so because of that, this works. And now f prime of c is f of 4 minus f of 1 over 4 minus 1. So you plug in, class. You replace the x with 4, you replace the x with 1, you do the math, you end up with 1. Now you have to differentiate this. 5 minus 4 over x. I hope everybody is okay with that. Minus 4 x to the power minus 1 is minus 4 times minus 1 x to the power minus. So I hope you realize this is elementary. You know how to calculate this. So f prime is this. Set that equal to this. I'm assuming nobody has any problem differentiating. And therefore, x squared equals 4. X is plus minus 2. So there are two answers. Now let's go back to the given 1 to 4, 1 to 4. Positive 2 in between, yes. Negative 2 in between, no. So there is only one answer, namely 2. So I hope everybody's fine with that. Let's look at one more example involving this idea of the Rolle's theorem, the mean value theorem. Suppose f prime is between these two numbers for all x. So right away, the fact that f prime is between these two numbers, that means the function is differentiable everywhere. And if it's differentiable, therefore it's continuous. So right away, with the mean value theorem, the first intact because of this. This statement says the function has a derivative always. Okay. So we're going to develop on that. So, and we go from, so we want this one. That means we're going to go from 2 to 8. That means A is 2 class and B is 8. So when you look at this statement, we want to show this. So we're going to go from 2 to 8. A is 2, B is 8. So we have A, we have B, and we have the first two. So the first two because of this statement. Okay. So we know this is the case. We also know this is the case. So we're going to find that one also. So according to the mean value theorem applies. We start with this. F prime is always between 3 and 5. So what is f prime of C? Let's calculate that. F of B minus F of A over B minus A. And as I said, we're going to go from 2 to 8. So why don't we plug in 2? Why don't we plug in 8? Calculate F of B. That means F of 8 minus F of 2 over 8 minus 2. We are going to calculate this. F of 8 minus F of 2 over 8 minus 2. What is 8 minus 2? 6. So replace this with number 6. 6 is a positive value. Multiply all sides by number 6. This becomes 3 times 6, 18. 5 times 6 is 30. And that's a proof. I want to quickly look at the last question, graphing. The function is increasing where f prime is positive, decreasing when it's f prime is negative. A critical point, as it was mentioned, you find f prime set equal to 0 or f prime doesn't exist. When you look at the top or the bottom, okay, peaks and valleys, you end up with local extrema. A function is concave up where f prime is positive. That means f prime is increasing, and concave down where f prime is negative or f prime is decreasing. An inflection point where concavity changes. So you have to find f double prime and do a sine graph on that. So what do we mean by that? Let's look at this example. By the way, as far as graphing, if you were to graph this by hand, class, you would find the intercepts, you would look at the end behavior. I hope you realize that the end behavior is, see, x, let me just do the drawing. For x cubed looks like this. Y equals x cubed. For y equals minus x cubed looks like this, as far as the end behavior. So you have the end behavior, you find the x-intercept, you put them all together, you have a rough sketch. So it's really not that big of a deal if we were to graph it using pre-calculus. Now let's see what we do with calculus. Let me erase this. So there is a way to calculate it, to graph it fairly fast. Let's find the intercepts by taking negative x out, and now you set this one equal to 0, class, x becomes 0. To set this one equal to 0, use the quadratic formula. Assuming everybody remembers that, I'm going to mention it. Minus b plus minus the square root of b squared minus 4ac over 2a. Everybody remembers that. That's elementary algebra. And here's what we get. Therefore, we have 3 intercepts, 0, 0, 1 plus square root of 5 over 2, 0, 1 minus square root of 5 over 2, 0. So if you put those 3 together with maybe a couple more points on the end behavior, you have a rough sketch. Now, going with calculus, we are going to differentiate in order to come up with intervals of increasing, decreasing, and doing the first derivative test. So minus 3x squared plus 2x plus 1. You can, it's a good practice to take the negative out and then factor this. I'm assuming everybody's okay with that, taking the negative out and factoring and setting it equal to 0, f prime equal to 0, x is 1, x is negative 1/3. We are going to do the sine graph on that. So when x is negative 1/3, f prime is 0. When x is positive 1, f prime is 0. If you look at this function, one of the things I want to tell you, class, nothing repeats and the exponents, none of them is even. Therefore, the result will alternate. The easiest point would be in between, which is 0 as a test point. If I pick a 0 and plug it into this, let's see what happens. 0. This becomes negative, this becomes positive. And with this negative, negative times positive results in positive. These two alternate. Yes, look at the arrows. Down arrow, up arrow. That means what? Decreasing, increasing, decreasing. So local mean occurs at x equals minus 1/3. Local max occurs at 1. And you have to plug minus 1/3 into the original function. Also 1 into the original function to find those relative extrema. So here we go. Local max is 1 at 1, 1. So plug in 1, evaluate it. Plug in negative 1/3 gives you negative 5/27. I leave it for you to evaluate that. So it's increasing from a negative 1/3 to 1. It's decreasing from negative infinity to negative 1/3, union 1 to infinity. So we have intervals of increasing, decreasing. We write what we found from the previous one, the steps and everything. And now we're going to go to f double prime. Here's f prime. Prime gives us negative 6x plus 2. When we set this equal to 0, x becomes positive 1/3. That is a possible point of inflection. We are going to do the sine graph. An easy point to the left of 1/3 would be 0. If you plug in 0, clearly gives you positive 2. So positive, negative. That means it's concave up here, negative infinity to 1/3. Concave down here, negative, that's what it means, from 1/3 to infinity. So at x equals 1/3, we have the IP or inflection point. Put it back into the original function. So concave down, concave up, inflection point. If you plug in 1/3 into the original function, gives you that point. So let's quickly recap by reading the summary of the pairs and look at each one accordingly and see what happened. The first, x-intercept at 0. 1 minus square root of 5/2, it's about negative 0.62 or negative 0.60. And the reason we write it in this format for the sake of graphic. The other one, 1.620. Maximum occurs at 1, 1. And we're going to put an arrow, meaning it can't cross that. The IP inflection point, again, 0.33, 0.41, because it makes it easier to show it on a grid. Minimum occurs again with the decimals. And remember the end behavior. So we go from here, hit the x-intercept, the minimum, the second x-intercept, IP, we go up to the local max, we bring it down to the last point, and this is the graph.